We want to talk about logistic models in this video, and this is just another kind of differential equation, special differential equation that'll come up. A logistic model is similar to an exponential model, where the models have a rate that's proportional to the function or to the population. However, it's also proportional, or inversely proportional technically, is it inversely? No, it's not inversely proportional. It's inversely proportional to how close it is to a maximum value, which is also known as carrying capacity. And so this is most commonly used in a natural environment. So if you're wanting to see like how many animals can live, how many animals do you expect to see in this field over time? So the general form is this right here. dp by dt equals some rate, this is the proportionality constant, times the population, but times 1 minus the population divided by k, which is the carrying capacity. So I just want to talk the logic here real quick. So what this is saying is if there's more animals, we'd expect, or if there's more of the stuff, we'd expect it to increase faster. More P, more dP, dt. But if we get to the carrying capacity, meaning we can't add anything else, if P equals K, then K over K is 1, 1 minus 1 is 0. So if we get to our carrying capacity, it doesn't increase anymore. If we don't have anything, it doesn't increase anymore. But if we're farther, the closer we get to our carrying capacity, the closer P gets to K, the less we get here. Or in other words, as far as the carrying capacity is concerned, if there's lots of space, if P is very small compared to K, then 1 minus that, we get a very large value here. It's basically entirely dependent on the population. So that's the kind of logic here, is if P is very far from K, it increases essentially exponentially. But as P gets closer to K, it slows down uniformly. So the general form can be solved with partial fraction decomposition, I believe. Yes. Just checking my notes. And I'm going to run through this general solving really, really quick. I encourage you to pause, give it a shot, but ultimately you don't need to know this. You're not responsible for knowing how to get the solution. I don't believe you're actually even responsible for knowing the solution, just understanding this as a differential equation. So first I'm going to do is I'm going to separate it or rewrite this as Rp times K minus P divided by K. And the reason I'm writing like that doesn't, well, we're writing it this way because it ends up being the way that lets you solve it nicely. Do you need to know why or how they thought to rewrite it this way? No, just these are equal. You can check the algebra if you're unsure, or you can just take me at my word here. So what we do is we separate the variables using this setup. And clearly I don't have this memorized as I'm checking my notes. Like I said, I don't expect you to either. So it's just basically pulling this bit here onto the left side, the other to the right. I'm skipping over the partial fraction decomposition, but you can double check it. You should end up with 1 minus P plus 1 over K minus P dP. And then on the right, we're going to have RT plus a constant. This ends up giving us ln of p minus ln of k minus p is equal to RT plus C. That gives us P over K minus P. Those would normally be in the natural log, but I'm also going to raise both sides to E at this point. And you've seen before where E to the RT plus C gives CE to the RT. And then we can write P is equal to CE to the RT times K minus P. And then if I plug in T equals 0, P equals P naught, that will give you, if you work through the algebra, again, I'm skimming through this real quick, but I want you to see the general trend of it. And if you want to check it, you'll have the main steps to double check. That gives us P naught is equal to C e to the E naught K minus P naught. And that's where we get this C is equal to that. And then you can come back to the doing a little bit more algebra, cleaning up, blah, blah, blah. You'll get P naught times the carrying capacity E to the RT over K minus P plus P naught E to the RT. And this should also be a P naught. So this is the solution. So at any given point in time, this is how many how much you would have based on the various values. Again, P naught is the initial population, K is the carrying capacity, R is the rate, the growth rate, and T is the time. Do you need to know this equation? Absolutely not. You do not need to have this memorized. In theory, I suppose they could ask you to solve it because it uses skills that we've learned. But broadly speaking, I just want you to see another example of solving a differential equation and give you maybe a challenge problem you could practice with. So let's look at some examples. The population PT in a fish pond satisfies the logistic differential equation. dP over dt is equal to P times 4 minus P over 6,000. I'm going to write the general differential equation up here, or the general logistic differential equation up here for reasons that will make sense in a second. What equation PT, or what is the carrying capacity? Well, if we can somehow get the equation down here into the form up there, we'll know the carrying capacity just by looking at the equation. And this is how most of what we're going to do here will work. So the problem that I have is I shouldn't have a 4 right here. So I need to get rid of that. I need to factor out a 4. So dP by dt is equal to 4p times 1 minus p over 24,000. Because again, if I'm factoring out a 4, divide both by 4, so that's the same as multiplying the denominator by 4. And now we see that k equals 24,000. What is the equation PT? You're not expected to calculate this if it ever came up. It's, I think, basically only in Khan Academy problems. But just go through and use the general equation, or the general solution that's known. Or if you are doing this in the real world because it's a defined thing and the solution is known, we just take all the values we know from the differential equation and plug them in here. So P naught is 8,000. The carrying capacity is 24,000. The growth rate R is 4. And then we divide by 24,000 minus 8,000. I'm just going to write that as 16,000. So it's a few less numbers to write, few fewer numbers to write. P naught was 8,000, e to the 4t. So that's how many fish will be there at time t. All right, one more quick example. In a given forest, the carrying capacity for a population of deer is 2,000 members. What if the population has a growth rate of 3 and an initial population of 5,500? What is the equation PET that describes the population of deer over time? Again, just using what we've talked about before. If you were curious, you can try writing the differential equation and the population function. You can pause here to give that a shot. Otherwise, I'll write them out here. So they said the growth rate was 3, so 3 times the population, and 1 minus the population divided by 2,000. So that's our differential equation. And then the solution is going to be our initial value, initial population, times the carrying capacity, times e to the growth rate times t, divided by the carrying capacity minus the initial population, plus the initial population times e to the growth rate times t. And again, it's just knowing the equation and telling from the function, from the problem, what values go where.